All right, so I just spent a lot of time going through recording this one, only to find out it had stopped recording. So uh, some of this, uh, some of this is already written out, and some of it I kind of just cleared and start over. But let's take a look here. So limits and continuity in higher dimensions. So we can say that a function f of xy approaches the limit L as xy approaches x naught y naught, and write this limit here. All right, the limit as xy goes to x naught y naught of f of xy equals L. If for every number epsilon greater than 0, there exists a corresponding number delta such that for all xy in the domain of f of x, or in the domain of f, f of xy, the magnitude of f of xy minus L is less than epsilon whenever our square root of x minus x naught squared plus y minus y naught squared is between 0 and delta. So this is very similar to our definition of a limit from way back before. Okay, so let's take a look here and see what we can do here after. So after this, we've got some properties of limits, and again, these properties are very much just extensions of the properties that we had for limits before, with summing them as just the sum of the limits, and the difference of them is the difference of the limits and products, and so on and so forth. And then the constant multiple is just the constant multiple times the limit. And then we can use the quotient rule where the limit of where we have a quotient like that is just the limit of the numerator over the limit of the denominator like that. And of course, then the power rule, provided we get a real number there, is that it's just the limit of whatever's inside there raised to that power. Okay, so let's take a look at some examples. These ones are pretty nice because you can just plug in 0 and 1 and you don't get anything. You're not dividing by 0. You don't get any of those indeterminate forms. And so you just plug in 0 for x and 1 for y in this first one, 0 for x, 1 for y in that one, and you'll get a -3. For the second one, you plug in that 3 and that -4, and you just plug them straight in and you get 5. So pretty simple limits there. Here, this one's a little trickier because if you try to plug in 0, 0, you get an indeterminate form, but like before, if you can do something to get it into a form where it's not indeterminate, do some algebra, then we're good. So we can make an equivalent form by multiplying the top and bottom by x, or the square root of x plus the square root of y. And by doing that, we can actually end up canceling out the x minus y here, and then we get a form where we can actually plug 0 in, and we don't get a 0 over 0 or anything like that. We don't get that indeterminate form. And so we just get that the limit is 0 there. Okay? And so that's fine. We are allowed to do that. So let's take a look here at this one. Again, I did this on the previous one, but it stopped recording shortly after this. So, well, not too short. It's a few minutes later. But anyway, let's go through this one. I'll circle was what I did. So as x goes to 0, our function is going to go to 0. That's going to be the case without having any issues, no matter what y is. And as y goes to 0, whatever x is some non-zero thing, then the function is go to 0. So for both of them, they go to 0. So that means that if we have a limit, then that limit is going to be 0. But I notice I said if we have a limit, then it's going to go to 0. And that's supposed to be equals 0. Okay, so if we do, it's going to be that. So let's see if we have a limit. So let's go back to our limit definition. So we're going to let epsilon be some number greater than 0, and it's given. So it's just some number we're picking. And we're going to find that corresponding delta that is greater than 0. And if we can do that, we can find the delta being greater than 0, then we know that we have a limit that exists. So we start with our limit definition: 4xy squared over x squared plus y squared minus the limit. And we said if the limit exists, it has to be 0. Well, that has to be less than epsilon whenever this is true for delta, that delta is greater than the square root of x minus x naught squared plus y minus y naught squared. And of course, we're plugging in the corresponding x naught and y naught, which I color-coded there with yellow and blue, with up there where we're taking the limit. And that has to be then greater than 0. And so if you look at our 4x squared, y squared, x squared plus y squared, this part right here, that is greater, or when we take the absolute value of that, we can get rid of this 0. We don't have to worry about that. But when we take the absolute value about that, y squared, x squared, y squared, 4, those things are all positive no matter what. So we can actually put the absolute value just around the x right there, and then have that be less than epsilon. And then when I just eliminated the y minus 0, I just made y squared, and x minus 0 made x squared. So I just got rid of those zeros. And so there's my requirement for delta. Since y squared is less than x squared plus y squared, right? It has to be, because x squared is going to be a positive number. That means that what we have here is we have 4 times the absolute value of x times this other little part, where y squared is smaller than x squared plus y squared. That means that y squared over x squared plus y squared part of it is actually smaller than 1. And so that means that when we take 4 times the absolute value of x and multiply it by a number smaller than 1, we're getting a number smaller than 4 times the absolute value of x. And we can rewrite 4 times the absolute value of x as 4 times the square root of x squared, because the squaring gets rid of the negatives or anything, and then we square root it and we're back to the same magnitude. And then that has to be less than or equal to 4 times x squared plus y squared, because y squared has to be greater than or equal to 0, and therefore that's going to be greater than. And if you notice, that's our x squared plus y squared. That's what we have right there. So we can go ahead and choose a delta. If we say we want to pick delta equals epsilon over 4, because we have that 4 there, we can then go right back and go straight through this. So this is our, this is right, that's that from right here, where we had that, our function minus the limit. It has to be less than what we found here, which was less than or equal to that 4x squared plus y squared square rooted. So less than that, which then that x squared plus y squared is less than delta. That's this part right here. It has to be less than 4 times delta, because all we did was add that 4 times it in front of it. And 4 times delta equals 4 times epsilon over 4. And if that's the case, then that just equals epsilon. So we do have an actual corresponding delta that will work with our epsilon. So whatever epsilon we pick, we can get a corresponding delta that is greater than 0 and greater than our requirement here for that. And so it works. And so therefore we have a corresponding delta, and the limit of this then must actually equal what we thought, which was 0. All right, let's take a look here. Our continuity definition, so a function f of xy is continuous at the point x naught, y naught if, 1, f is defined at x naught, y naught. If it's not defined there, like say in this example here, then it's not continuous if there's a break there. But if it's defined like in this one, and the limit exists, so we can actually take a limit, it goes there, and the limit is actually equal to the value at that point, then it's continuous at every point it's domain. As long as that's true for every point, then it's nice and it's continuous. Okay, so here's one again. I already did out, but let's go through it. So this says show that f of xy equals this this piecewise function here, where we're defining at xy where our 2xy over x squared plus y squared wouldn't be defined. We're going to define that as 0. Now, is continuous at every point except the origin. So that's what we want to show. Well, showing it's continuous at every point, ignoring the origin for a second, is pretty easy, because you can just pretty much plug any non-zero numbers into there. So any point you want, 1, 1, 5, 5, 1, 5, negative 100, negative 100, whatever, you can plug in there. And then you can just actually work it out, and you'll get something that works, that is actually not an indeterminate form for a limit. So that part's pretty easy. But what about at 0? So let's take a look at this. Let's pretend we're going to look at this along the line y equals mx. So remember, this is some surface that we're moving along, and we can travel along this 3-dimensional surface, right? So we have some 3-dimensional surface, whatever it happens to be. We can travel along like that path, or we could travel along this path to go towards the same points. All right, so we're going to travel along some different paths along there and then see what happens here. And so we're going to go ahead and just look at the path y equals mx. So this is the family of straight lines of slope m. So whatever the slope happens to be, we'll travel along that. Okay, So let's take a look here. If we say that is true, we can say that we can evaluate it at y equals mx. And when we do that, we substitute in that mx here and here for x. And then what happens is we can cancel all these x squareds. And we end up with 2m over 1 plus m squared. And that's a constant for that given value of m. So whatever, as long as we're traveling along a specific line, so we pick a specific slope, we travel along, say, 2, then every value along there is 2. And therefore, it's a constant, which also means that that's what our limit has to be. So therefore, as we approach 0, 0 along one of those lines, the limit has to be equal to whatever that value is for that line, whatever that constant value is as we go to it. Now, the problem is that since that's the case for our limit here, right, that's what our limit has to be, because there's no other values on those lines, the problem is for different values of m, we're going to get different limits, right? So if I pick m is 1, I get 2 over 2, I get 1. But if I pick, m as 5, I get 10 over 26. And so I have different ones, and so different values of m give me different limits, and therefore, the limit does not exist. We can't have a limit exist if we can't even agree on what that actual limit is as we do it. It's different for every different path we look at. All right, and here you can see this. They're showing you the picture where, again, as you go towards different places towards there, you're going to get different values along that 0, 0 there, right? Because if I come in along, if I come along this path, I'm going to end up down here. If I come along this path, I end up here. And so I have different limits along there for getting to x and y are both 0, 0. All right, and then they're showing you that in the level curves, where as you come along those level curves, they have different values, different constant values along those level curves. And so therefore, again, if I come along that curve, I'm ending up way up here with my output value being z, and I come along this curve and I have this different output value down here. And if I come along this one, I have this different output value there at 0, 0. All right. This brings us to the two-path test for non-existence of a limit. So basically what this says is if a function f of xy has different limits along two different paths in the domain of f as xy approaches x naught, y naught, then the limit as of xy goes to x naught, y naught of f of x does not exist. And hopefully that makes some sense, because if you're coming in different ways to it and you're getting to there and you have all these different values, then of course you don't have a limit. So if you can find just two different paths that give you two different limits, then no limit. All right, so let's take a look at this example here. It says show that this function, similar to the previous one, but we have that x squared on the top now instead of just x, and it's an x to the fourth in the bottom, has no limit as xy approaches 0, 0. And so here the limit cannot be found by direct substitution, again, because you plug it in and you get an indeterminate form of 0 over 0. So we examine the values of f along the curves at 0, 0. And we're going to pick the curve y equals kx squared. And we pick that one because it's nice and it gives us a nice constant for along those curves. So if we plug in kx squared in there, you can evaluate it at kx squared. You can then plug in kx squared, distribute everything around, and then cancel out all your x to the fourth, and you end up with this 2k over 1 plus k squared, which is a constant. And so along any one of those curves that we follow, we end up having a constant value everywhere along that curve, and therefore that's what our limit has to be. So as we move along that curve, that limit stays that constant value, and therefore that's what we have, a constant value. Now the problem here is for different values of k, just like we did in that previous one, different values for different values of slope. Here we have different values of k. We're going to have different limits along each one as we go towards 0, 0. For example, if you pick k equals 1, which moves you along the y equals x squared parabola, you end up with 1, or you end up with 2 over 2, and you have a limit of 1. But if you travel along k equals 0, which is just along the x-axis here, you end up getting a limit of 0. And so therefore there's two different limits based on there, and therefore it's different. All right, and you can see that here in the level curves where, again, it's kind of hard to see in that picture on the top, at least for me. It looks kind of like a jumbly thing. I don't know if I just have old eyes, but you can see down here in the level curves, you have different values there as you move towards it when you get to that 0, 0. Those are different constant values along them, and therefore you end up with different results as you travel along each one. Therefore, no limit existing there. So let's try a look at this one. Now this one, we can see here that along the curve y equals kx squared, we end up with what we had just did before. Y equals kx squared, we just did that one. We found all those constants, and it was no limit as we went along. So let's take a look then at the path y equals mx. And so if we just do this kind of quickly, because I know this video is dragging on, but if we evaluate f of xy at that mx, right, at y equals mx, y equals mx, we end up with 2x squared and then mx over x to the fourth plus mx squared. This just equals 2mx cubed over x to the fourth plus m squared x squared. We can cancel out an x squared from everything, and we end up with a 2mx over x to the fourth plus m squared. And so if we look at that, we see that we don't have a constant here. But as we go along those curves, this is what our value approaches. And so therefore, if we take that limit of this right here, if we look at the limit of this as we go to 0, you notice that every time we get a limit of 0. So no matter what value of m we pick, say if we pick m as 1, it's 2x over x to the fourth plus 1. If we pick m as 2, we get 4x over x to the fourth plus 4. If we pick m as 3, we get 6x over x to the fourth plus 9. But anyway, the point is the limit of all of those, as we go to 0 for x, they are all 0. And so this is where you have to be careful. Basically, if we have the same limit along all these straight lines here, right? These are the straight lines we're looking at, approaching some value, x naught, y naught, this does not imply that we actually have a limit that exists, because we already saw that this function doesn't have a limit exists. But if we look at this one and we start taking the limits of these limits, right? Limit, they're all going to give us 0, right? All these have limits of 0, so you have to be careful with that, all right? So straight lines approaching does not imply that the limit exists. You got to look more than that. You can't just look at just this and say, oh, they're all 0, so therefore the limit exists. Okay, you're really looking to try and find a way to disprove that the limit exists instead of trying to have something that shows the limit does exist with this. All right, so here we've got continuity of composites. So here, if f is continuous at x naught, y naught, and g is a single variable function continuous at f of x naught, y naught, then the composite function h equals g of f defined by h of xy equals g of f of xy is continuous at x naught, y naught. Okay, so just if we're continuous on f of x naught, y naught, and then the composite basically is going to be continuous at that point as well. Okay, and then I think this is our last page. Yep. So here, functions of more than two variables. Basically, this is just going to tell us that the stuff we did, it extends out to more than two variables. So the definitions of limits and continuity for functions of two variables, and the conclusions about limits and continuities for sums, products, quotients, powers, all that stuff, all extend to 3 or more variables. And so you can do that. And then there's just a little examples there of it extending out. Okay, that's pretty much it for this section. And then we will start in the next section next time, where we're starting these partial derivatives with that nice messed up graphic. All right, that's it. Thanks for listening.